Hello everyone, this is the third lecture on quantum mechanics. Today we're going to talk about momentum. So, for a particle in state psi, we've defined that this bracket x, the expectation value of x, is a whole space integral of x produced by this probability density, psi norm squared, and this psi norm squared is also can be computed by this form. So here is a question. What does it mean? This bracket x, the expectation value of x. Experimentally, there can be two answers. Here, one, the average of x of a particle measured by over and over again. Here is first situation. There is one particle and there is a psi state wave function, and we observe them and get x1, and again observe them, we get x2, and then we average all of them. Or there can be another situations like 2 for many isolated particles which are in the same state psi, the average of x of them. So here there are n particles with the same psi state. Particle 1, particle 2, particle 3, particle n, they are all in the same state. We call this group as an ensemble of particles. So we observe the particle 1 to get this x1, x2, x3, and so on, and then average them. The right answer is 2. The meaning of the bracket x is exactly corresponds to this 2. So do not misunderstand this meaning of bracket x as first one. This is not true. Okay. As a conclusion, the expectation value is the average of measurements on an ensemble of identically prepared systems, not the average of repeated measurements on one and the same state. I mean, the same system. So, since here bracket x is integrated by this x variable, so the bracket x is a function of time, t. So we can think of this. Is there any concept like velocity in quantum mechanics, such as for the classical mechanics? There is some analogies, and here is that. So we can ask how fast the bracket x moves. But don't misunderstand. You cannot think the wave function as a particle itself, and the particle is moving in some velocity, which does not make sense. So do not misunderstand this concept. So here we differentiate this bracket x with time variable t, and boring calculation is going on. So here we put this d dt inside the integral, changing to this partial t, and then we use the product rule like this, and then we recall the Schrödinger equation and then plug in and so on. We used integral by part, and then also integral by parts, and we get this massive calculation to get this. Okay, this was just a calculation, so you can do this or not, just practice. As you can see from lecture 1 or from lecture 2 and from this lecture, there are many techniques for integral, especially there are a bunch of integral by parts. So remind you that you have to use sometimes or somewhere, somehow, you have to use the integral by parts. This is tip. So as a conclusion, not quite exact notion, but the velocity of wave function, more precisely, velocity of the expectation value of x is minus I haba divided by m integral psi conjugate, and this partial x psi dx. Don't misunderstand this concept. The velocity of the expectation value of x is not the velocity of a particle. We cannot think in quantum mechanics the wave as a particle. Okay? It just all we are able to know is that of the concept of the probability. So here it's not clear that what velocity means in quantum mechanics. If the particle doesn't have a determinate position, neither does it have a well-defined velocity. So here's a moral. All we could reasonably ask for is the probability of getting particular value. So only probability matters. And here is very intuitive and familiar form also applied to this quantum mechanics. The expectation value of V is equals to time differentiated expectation value of x. Also, we can use by analogy in classical mechanics the expectation value of p, which is momentum, is m bracket v. Here bracket v is d bracket x dt, and plug in. Where was it? D bracket x dt. Here. When you plug this in here, you get this. As a conclusion, we summarize the conclusions like this. When you find this bracket x, the form is like this: integral and psi conjugate x and psi and dx. Also, the bracket p is of the form like this: integral this psi conjugate and psi dx, and this minus I bar partial x is sandwiched by this guys. So we can think of this unique guys as operator and the other guys as a shell. So here's a very fun thing about the operator. So here's a sandwich method. This is not official terminology, but I can name this method as sandwich method. So do not use it officially or your paper or something like that. So position operator is x, momentum operator is minus haba partial x, and we sandwich them. If we sandwich them with this guys, integral psi conjugate and psi dx, we get the expectation value. Simple. This guy is here and sandwiched by this guys, and we get the expectation value of p. So memorize this operator. The simple position operator is just the position x, and momentum operator is minus I ha bar partial x. In classical mechanics, all dynamic variables can be expressed in terms of x and p. You know that, such as this kinetic energy T is 1/2 mv squared, and this is equals to p squared divided by 2m, which is kinetic energy. Also, this L, the angular momentum, equals to r cross product with mv, which is rp. So every dynamic variables can be expressed in terms of this position and momentum. This situation in classical mechanics informs us about the analogy to this quantum mechanical situation like this. So here's a theorem. So any quantity and bracket here, which means expectation value of this Q, can be calculated by this simple form sandwiched method. So here is bread guy, and here is something meat or tomatoes or something like that, cheese. So here guys, sandwich this guys, and you get the expectation value. But one thing you have to notice that this P should be changed to this momentum operator. X itself is momentum operator, so we do not change this X. Okay. Great. So here's an example. The expectation value of kinetic energy T equals to T expectation value of Txp equals to expectation value of P squared over 2m. This is just constant, so popped out. The remaining thing is the bracket P squared, and we just use the sandwich method like this. Here are the guys, bread guys, and here are the cheese guys. So we can very simply calculate the expectation value of any variable in quantum mechanics by this method. Great. So we're gonna solve one problem, and this problem is very massive in terms of the calculation or computation. It needs very long process, so I was exhausted with solving this problem, but I did it, so you can do it also. So here is very simple question. Calculate the ddt bracket p. So use the definition, use the sandwich method. You have to remember the momentum operator's structure like this, minus I haba partial x, and sandwiched by this guys, bread guys. Go on, and then we differentiate both side by this t and get this, blah blah blah, canceling out. And then you know that the psi must go to 0 when x goes to plus minus infinity. Go on, go on, go on, go on, go on, go on, not yet. We used a vast amount of the technique like integral by part with calculating this simple question. So go on, go on, go on. Here is last. Here's last, last integral by part. So we get this. As a conclusion, the time derivative of this bracket p equals to bracket minus partial v partial x. But, in classical mechanics, we know this. What is this? The time derivative of p equals to force. And force is equal to this minus time, not time, I'm sorry. It should be x space differentiate here. So v differentiated by x, and this v is potential, and this is the formula what we expected in classical mechanics, and it has same structure in quantum mechanics too. So actually there is a theorem, very famous theorem by, I don't know how to pronunciate this name, Ehrenfest, like that, Ehrenfest theorem. So expectation values obey the classical laws, and here we have a classical law, and we can convert it to the quantum mechanical law like this. So here's a note. In classical mechanics, the zero of potential doesn't matter. Only difference thus, we know that in classical mechanics, only difference of the potential energy matter. But in quantum mechanics, is not the true. We can check by this easy step. So first of all, we write down this Schrödinger equation, and then we put this v replaced by v plus v0, but these two terms are not equal, right? Because here same, but here same. This remaining term make this equation is not true. So we have to change the psi form to satisfy this equation. The good guess is like this: psi exponential v0t divided by I bar. How can we check this? Just plug in, then plug here in, and then check, and you get exactly same outcomes. So here, as a conclusion, different from classical mechanics, if v is replaced by this v plus v0, then psi should be replaced by this psi product exponential of minus I v0t divided by bar. So don't misunderstand this term. Here 1 over I equals to minus I, so I change this as minus I. So here is a crucial difference between the quantum mechanics and classical mechanics. In classical mechanics, the difference of potential energy doesn't matter in classical mechanics, but in quantum mechanics, the difference of potential energy matter. I mean, the zero point of potential energy matters. So when we change the potential, the psi is changed also by the multiplicative term is attached to the psi as exponential minus I over half bar v0t. And you will see this form very usually. So remember this form, minus I over half bar v0t, and that's it. Okay, to recap, today we were talking about the momentum. So we studied this meaning of the bracket x expectation values meaning. It's not the first case, the average of x of the particle measured by over and over again is not true. But second case, for many isolated particles which are in the same state psi, the ensemble state, right? The average of x of them is true for meaning of this bracket x. Then we introduced the notion of sandwich method to find the expectation value of some quantity. You have to memorize this operator, position operator x and momentum operator minus I half bar partial x, and then we sandwich them to get the expectation value with integral psi conjugate and psi dx. Any other quantum mechanical quantities is generally found out by this formula, sandwich method. You have to change the p to the minus I half bar partial x, which is exactly the form of the momentum operator, right? So here, this formula is a recipe for computing the expectation value of any dynamical quantity for a particle in state psi. And we solve one problem like this. Very exhausting process. What's going on? And we get this very similar form of equation which resembles an equation from classical mechanics, and this leads to the notion of Ehrenfest's theorem. Expectation values obey the classical laws. And here's remaining part. The only change of energy matters in classical mechanics. However, in quantum mechanics, the 0 point, the zero of energy also matters, which that brings the additional multiplicative term exponential this minus I half bar v0t. That's it. So if you enjoyed it, please subscribe and like. And I was tired today, so I think I was not good at lecturing. But if you enjoyed it, please subscribe, and most of all, enjoy the physics. Bye bye.